Hello everyone, welcome to lecture on Newton's rings. I am M. Satyavani, lecturer in physics, DNR College, Bhimavaram. In previous videos, I have discussed about the phenomenon of interference and the formation of interference fringes. In that video, I have discussed about types of interference. In that case, there are two types: interference by division of wavefront and interference by division of amplitude. This division is to produce coherent sources. In these two types, Newton's rings belongs to interference by division of amplitude. That means a single source of light is taken and the rays from the source is divided into two rays having equal amplitudes by the phenomenon of reflection, and the two reflected rays act as two coherent sources and they interfere with each other and interference fringes are produced. In this experiment, Newton's rings experiment, interference fringes are formed by the method of interference by division of amplitude. Now I discuss about the formation of Newton's rings. In Newton's rings experiment, the experimental setup is as shown in the figure. This is a plano-convex lens. That means a lens having a plane surface. One of the surface is plane and the second one is a convex surface. This is a plano-convex lens, and this is a glass plate. When a plano-convex lens of large radius of curvature or focal length is placed with its convex surface in contact with the glass plate, a thin film of air is enclosed in between convex lens and plane glass plate. This is a plano-convex lens and it is placed on this plane glass plate. Then there is some space in between plane glass plate and the plano-convex lens. Then a thin air film is formed in between these two surfaces. Here at the contact, the thickness of the air film is 0. The thickness of the air film gradually increases from center to the ends. If you consider at one point, this is the thickness of the film. The locus of all points having the same thickness of air film is a circle. If you join the points having the same thickness of the air film around the convex surface, you get a circle. Different thicknesses corresponds to different circles. Suppose a monochromatic light is incident on it normally. A part of it undergoes reflection. Suppose this is a monochromatic source of light. When it is incident on it normally, a part of it is reflected at the curved surface of the plano-convex lens. That means at the boundary of glass and air film, and a part of it is reflected. The first reflection takes place at the convex surface to air film. Then this transmitted ray again undergoes reflection at the plane surface of the plane glass plate. This is the second reflected ray. These two rays, R1 and R2, are derived from the same incident ray. This is the incident ray. These two rays are derived from the incident ray. That means these two rays act as two coherent sources. They are derived from the same incident ray and they have travelled over different paths. First ray, the distance travelled by the first ray is BR1, and the second ray distance travelled by the second ray is BC plus CR2. Therefore, they have travelled over different distances. So, they are derived from the same incident ray, They act as two coherent sources and they have traveled over different distances. Therefore, they are in a condition to interfere and interference fringes are formed. These fringes are alternately bright and dark circular rings. Circular rings because the locus of all points having the same thickness of the air film is a circle. Different thicknesses corresponds to different circles. Therefore, different circular bright and dark rings are formed. This phenomenon was first observed by Newton. Therefore, they are named as Newton's rings. That is about the formation of Newton's rings. If, for example, if this is the thickness at one point, and then we know that in thin films, in the theory of thin films by reflected system, in reflected system, the path difference is 2 mu t cos r plus lambda by 2. Mu is the refractive index of the thin film and t is the thickness of the thin film. R is angle of refraction and this lambda by 2 is due to Stokes principle of reversibility, which is when the reflection takes place backed by a denser medium, then there is an extra path difference of lambda by 2. In this video, there are two rays. This is the first reflection and the second reflection takes place at the point C. The first reflection is from glass to air, therefore that is from denser to rarer. The second reflection is from rarer to denser. Here the reflection takes place backed by a denser medium as glass is denser than air. Therefore, there is an extra path difference of lambda by 2. In case of thin films, the path difference between the two rays is 2 mu t cos r. We have already derived. Then there is an extra path difference of lambda by 2 due to phase change on reflection. Therefore, total path difference is 2 mu t cos r plus lambda by 2. In case of an air film, mu is equal to 1. For air, refractive index is equal to 1. Therefore, for air film, mu is equal to 1. And for normal incidence, that means when the rays are incidenting on the combination perpendicularly, then angle of incidence is 0 and angle of refraction is also equal to 0. If you substitute these two values, that is mu is equal to 1 and r is equal to 0, then this equation becomes 2t. Then when r is equal to 0, we know that cos r is equal to 1. Then this equation becomes 2 into 1 into t into 1 plus lambda by 2, that is equal to 2t plus lambda by 2. That is the total path difference in case of Newton's rings experiment. At the point of contact, that means when the convex lens touches the glass plate, then at the point of contact there is no air film, then the thickness is 0. Then the path difference becomes T0, then 2 into 0 plus lambda by 2, that is equal to lambda by 2. We know that in the theory of interference fringes, when the path difference between the two interfering rays is equal to odd multiple of lambda by 2, we get dark ring. Therefore, this path difference lambda by 2 is the condition for minimum intensity. Therefore, dark spot is observed. Therefore, the central spot in Newton's rings experiment is dark. Next, if 2t plus lambda by 2 is equal to n lambda, bright ring is formed. This is the condition for bright ring, where n is equal to 1, 2, 3 and so on. If 2t plus lambda by 2 is equal to 2n plus 1 into lambda by 2, dark ring is formed. These are the conditions for the formation of bright and dark rings. This is the general condition. Next, the next topic is determination of diameter of the ring. In Newton's rings, these are Newton's rings. This is the central dark spot, alternate bright and dark rings. These are the circles, concentric circles. This is the center of the circle. This is the first bright ring. This is the radius, and in this way the radii of different rings varies from center to ends. Gradually the radius of the first ring is less than radius of second ring, and so on. Therefore different rings have different radii and different diameters. For example, if you consider this ring, this is the third bright ring, and we have to determine the diameter of the ring, and for this purpose consider a convex lens, plano-convex lens. LOL dash is the plano-convex lens, and this is the plane glass plate. We know that lens is nothing but it is a spherical surface. Then it appears to be taken from it is a part of the sphere. Then if you close this surface, you get a sphere. This dotted line indicates the sphere from which the lens is taken apart. This is the radius of the sphere from which the lens is taken apart. This radius is called as radius of curvature of the lens. Radius of curvature is nothing but the radius of the lens from which the lens is taken apart. This is the sphere from which this lens is taken apart. This is radius of the sphere. This is also called as radius of curvature of the lens. For example, if you see this figure, OC is radius and OD is diameter. We know that diameter is equal to 2 times radius. Next, this is diameter, and this is also this is a chord in this circle. From the properties of circles, when these two chords intersect each other, then O, if you consider thickness T, suppose R is the radius of curvature of the lens and thickness of the air film is T at this position for a certain ring, then this is the circle. This is a two-dimensional figure, therefore we cannot observe a circle, but this is a circle corresponding to the thickness T. Then this is the center of the circle, therefore this is the radius of the circular ring. This is the NP is the radius of the circular ring. Next, when these two lines intersect each other, then according to the property of circles, then ON into ND. ON, the two parts in OD is ON and ND. ON into ND is equal to, in this case, QN into NP. This is equal to thickness of the air film T. Therefore, ON is also equal to T. The total distance OD is diameter, that is 2R. This part is T. Therefore, ND is equal to 2R minus T. ON is equal to T. OD is equal to 2R. As ON is equal to T, the remaining part ND is equal to 2R minus T. If you substitute the values of QN, NP and so on, QN, this is a circle which we have not observed in this figure as it is a two-dimensional figure. QN is the radius of the ring. Similarly, NP also the radius of the ring. Therefore, QN is equal to radius of the ring which we have taken, and NP is also equal to radius. ON is the thickness of the film, and ND is equal to 2R minus T, where R is radius of the sphere which is called as radius of curvature of the lens. Then R square is equal to 2RT minus T square. 2RT minus T square. In this case, we have taken a plano-convex lens of large radius of curvature. Large radius of curvature means that then it is almost just like a flat surface. Then the distance between the plain glass plate and the lens is very small. That means the thickness of the film is very very small. As t is small, t square is neglected. T square is very very small, therefore it can be neglected. Then this equation becomes r square is approximately equal to 2rt as t square is neglected. Then 2t is equal to r square by capital R. In case of Newton's rings, we have already said that the total path difference is 2t plus lambda by 2. Here 2t is equal to r square by r plus lambda by 2 is equal to n lambda. We get bright fringe, where here we are taking, for example, nth bright ring, then it is denoted by Rn, where Rn is the radius of the small rn is the radius of the nth bright ring. If you substitute the value of 2t, you get Rn square by r is equal to n lambda minus lambda by 2, which is equal to 2n minus 1 into lambda by 2. Finally, solving this equation, you get the radius of nth bright ring is equal to square root of 2n minus 1 by 2 into r into lambda. From this equation, we can say that the radius of nth bright ring is proportional to number 1 square root of lambda, that is square root of wavelength of monochromatic light, and the second one is Rn is directly proportional to square root of radius of curvature, and it is directly proportional to square root of 2n minus 1 by 2. This is the about radius of bright ring. If you double this value, you get diameter of the bright ring. This is the expression for radius of nth bright ring. We know that diameter is equal to 2 times radius. Then diameter of the ring is equal to 2 nth bright ring is equal to dn, that is equal to 2 Rn. Similarly, for a dark ring, the condition for dark ring is path difference is equal to 2n plus 1 into lambda by 2. Then if you substitute the value of 2t as above, you get radius of nth dark ring. This is the radius of nth bright ring. N means it may be either 1, 2, 3 and so on, as n is equal to 0. In this case, this is the radius of expression for radius of nth dark ring. This is the expression for radius of nth bright ring. We know that this means this radius of nth ring depends upon radius of curvature of the lens, wavelength of light used, and natural number n. From this expression we can say that in order to get the rings of large radius for good observation, radius of the lens must be large, because the radius of the ring small n, Rn, is directly proportional to square root of radius of curvature. As the radius of curvature decreases, radius also decreases, and we cannot observe clear Newton's rings. But for this purpose, we have taken a plano-convex lens of large radius of curvature, because radius for good observation, the radius of the ring must be large. As radius of the ring depends upon radius of curvature capital R, therefore we have to take a plano-convex lens of large radius of curvature. The next one, Rn, radius of nth dark ring, also depends upon wavelength of light, square root of wavelength of light used. As lambda increases, Rn also increases. Next, it also depends upon the square root of n. That means as the number of ring increases from center, radius also increases. If you take R1, that is radius of the first ring, it is equal to root of r into 1 into lambda root of r lambda. If you take the second ring, radius of the second ring r2 is equal to root 2 into root r lambda. If r3, similarly r3 is equal to root of r lambda into root 3. r1 is to r2 is to r3 is equal to root 1 is to root 2 is to root 3 and so on. That means we can say that the ratio of the radii of dark rings in Newton's rings is in the ratio of square root of n natural numbers. Next, from this equation we can calculate diameter. We know that diameter is equal to 2 times radius, therefore 2 into square root of Rn lambda. That is about diameters of bright and dark rings. The next one is determination of wavelength of sodium light using Newton's rings. We know that sodium light is a monochromatic light, and we are using monochromatic light in interference fringes. In general, in laboratories, sodium light is taken as monochromatic light. We have to determine the wavelength of sodium light by using Newton's rings. First of all, we will discuss about the experimental setup. The experimental arrangement for the formation of Newton's rings is as shown in the figure. This is a plano-convex lens of large radius of curvature. It is placed on a plain glass plate with a curved surface in contact with the, there are two surfaces for a plano-convex lens. It is a plane surface and the second one is curved surface, convex surface. It is placed such that the convex surface touches the plain glass plate. Then only air film is formed in between these two surfaces. And S is a monochromatic source of light, for example sodium light. The light from the source S is made parallel by means of this convex lens L1. When the light from S is incident on the convex lens, if S is placed at the focus of the lens, then the rays becomes parallel after passing through the lens. S is a narrow monochromatic source of light, and when the light from S is incident on this convex lens, these rays are made parallel. These parallel rays are allowed to incident on a plain glass plate G, which is making an angle 45 degrees with the path of the rays. It is inclined such that the rays angle of incidence is 45 degrees, because we know that in case of reflection, angle of incidence is equal to angle of reflection. When angle of incidence is 45 degrees, then the reflected rays are normal to the combination. For this purpose, for normal incidence, we are placing the glass plate G, which is inclined at an angle of 45 degrees. When these rays are incident at an angle of 45 degrees, then these rays becomes normal and these rays are allowed to incident on this combination. The next part is when this normal light is incident on this combination, a part of it is reflected at the curved surface and a part of it is reflected at the plain glass plate, that is on the upper and lower sides of the thin air film. Then these two reflected rays are derived from the same source, same incident ray, and they act as two coherent sources, and these two reflected rays interfere with each other. Alternate bright and dark rings are formed. These rings are observed through the eyepiece of the microscope. This is the experimental setup. This is the Newton's rings arrangement, and this is the narrow monochromatic source of light. The light from S is allowed to incident on this plain glass plate, which is making an angle 45 degrees with the path of the rays. Then they are reflected at 90 degrees. These normal rays are allowed to incident on this combination. Then each ray is divided into two reflected rays, and these two reflected rays interfere with each other and circular rings are formed. They are observed through the microscope M. Next, theory for the determination of wavelength of light. In the equation of radius of the ring, we have Rn is equal to root of capital Rn lambda, where R is radius of curvature and lambda is wavelength of light used. This is the expression for diameter of nth ring. If you take mth and nth rings, dark rings, then their diameter squares are dn square is equal to 4Rn lambda. Similarly, dm square is equal to 4r, in place of n it becomes m rm lambda. If you subtract these two equations, dn square minus dm square is equal to 4r lambda into n minus m, where dn square is the square of the diameter of nth ring, dm square is square of diameter of mth ring, 4r is radius of curvature, and these are the lambda is wavelength of light, n and m are number of the rings. We have to calculate the wavelength of light. Therefore, lambda is equal to dn square minus dm square by 4r into n minus m. This is the expression for wavelength of light in case of Newton's rings. Therefore, in order to find out the value of lambda, we have to determine the values of dn, dm, r. Next, experimental procedure. For the determination of diameter of the rings, travelling microscope is used. By using the travelling microscope, the travelling microscope consists of eyepiece having crosswires. Then, first of all, travelling microscope is moved from center to the left side, and the center of the crosswires is adjusted tangentially. That means the vertical crosswire is made to coincide with one of the bright rings, say 20th bright ring. The reading on the microscope is noted. By moving the microscope from left to right and by coinciding the crosswire with dark rings, that is 19th, 18th and so on, bright or dark rings, till we are very nearer to the central spot. First of all, the crosswire is made to coincide with 20th ring, next 19th, next 18th and so on up to 4 or 3, that is very nearer to the center. Then again by crossing every time the reading is noted. In this way, the readings of by coinciding 20th, 19th and so on rings are noted on the left side. Then again by crossing the central spot in the same direction, the readings corresponding to 4, 5 and so on 20th rings are noted on the right side. The microscope must be moved in the same direction to avoid backlash error. In each time the reading is taken, these readings are tabulated. This is the tabular form. We are taking the readings for each ring on the left side and right side. Left side and right side. Then the difference of the readings gives diameter. For example, this is the third ring. If you take the reading at this position and at this position on the left side, and similarly if you take this position reading in the right side, the difference of these two readings gives the diameter. This is the reading at this position and if you get the reading at this position, the difference of these two readings gives the diameter. This is the diameter. This is the line passing through the center of the ring. Therefore, difference of these two readings gives diameter of the ring. In this way, the diameter of each ring is calculated and the squares of the diameters are also calculated. Then a graph is drawn between order of the ring, that is number of the ring is taken on x-axis and squares of the diameters are taken on y-axis. You get a straight line passing through the origin. The values of dm square and dn square in equation of lambda are taken from the graph at different number of the ring. Then from this graph we get the values of n, m and the diameter squares corresponding to mth and nth rings, dn square and dm square. Next, in this expression from graph we can substitute dn square minus dm square by n minus m. In this expression, the radius of curvature r of the plano-convex lens is determined by using this parameter. The formula for radius of curvature is L square, r is equal to L square by 6h plus h by 2, where L is the distance between any two legs of the spherometer. H is the height of the spherical surface, and these two values are taken from the spherometer, and by substituting these values we get the value of capital R. By substituting the values of dn square minus dm square by n minus m from graph and r from the, by calculating radius of curvature using spherometer and substituting these values in this expression, we get the value of wavelength of monochromatic source of light. In this way, using this formula we can calculate wavelength of monochromatic light like sodium light. This is the experiment for the determination of wavelength of sodium light using Newton's rings experiment. Once again I conclude this experiment. Newton's rings are formed when a plano-convex lens is placed on a plane glass plate. Then different circular rings are observed when monochromatic light is incident normally, and this experiment is used to determine the wavelength of light lambda. If you know the wavelength of light lambda, we can also determine the radius of curvature of the plano-convex lens. This is about interference fringes formed in this combination, that is in Newton's rings experiment. In this case we have derived different conditions for diameter of the rings and expression for wavelength, etc. That is about Newton's rings. In general, in examinations we get the question like, what are Newton's rings? How wavelength of a sodium light is determined using Newton's rings experiment. That is the question generally in question papers. Therefore, that is the assignment for you. What are Newton's rings? How wavelength of monochromatic light is determined using Newton's rings. Thank you.